Before we learn our new stuff, let's look at our old stuff. Recall that we have seen how to do double integrals over rectangles. In those cases, we are presented with a double integral over r of f of x, y, dA, which is either the integral from c to d of the integral from a to b of f of x, y, dx, dy, or the integral from a to b of the integral from c to d of f of x, y, dy, dx. And in these cases, we could sometimes express the integral as a product of the integral from a to b of g of x dx and the integral from c to d of h of y dy. Now we have a subtle notational change that leads to a pretty big change. We're going to be looking at the double integral over a region D of f of x, y, dA. Notationally, R represents a rectangular region. D represents a non-rectangular region. Now, just so I can have parallel language here, we had the double integral over r of f of x dA, which is blah, blah, blah. Now we have the double integral over d of f of x dA, which is either the integral from a to b of the integral from g1 of x to g2 of x of f of x, y, dy, dx, or the integral from c to d of the integral from, got my letters confused, h1 of y to h2 of y of f of x, y, dx, dy. Here what we see is that the innermost, for the first one, the innermost limits of integration are functions of x, g1 of x and g2 of x. In other words, y goes from those two, from g1 of x to g2 of x. Y depends on x, and that's totally fine. X, the outermost differential, corresponds to the outermost integral, and it has constant limits. That has to be the case. Always, 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 the outermost integral has to have constant limits. In the case of the second one that we wrote, dx is the innermost differential. X goes from h1 of y to h2 of y, functions of y. And then dy, the second differential, corresponds to the outermost integral, which again has constant limits from c to d. Now back to our region R. That looked in R2 like, of course, a rectangle. And we would have said it's a rectangle that has limits on the x-axis that go from a to b, and on the y-axis that go from c to d. Now we're looking at a region D, and our author expresses them as a type 1 region and a type 2 region. The type 1 region is characterized by y having variable limits of functions of x. So y would go from g1 of x to g2 of x. Let's see what that looks like. Let's just consider two functions. We'll call this lower one g1 of x, and then an upper function here, g2 of x. And in this case, x goes from a to b. The type 2 region is the one that we can express using the order of integration dx dy, where x has variable limits from h1 of y to h2 of y. And that looks like maybe something like this, where we have a lower limit of integration function h1 of y and an upper limit of integration function h2 of y. And in this case, y goes from c to d. It's not out of the realm of possibility that we have a region that is both type 1 and type 2, and something that looks maybe like this, which is maybe like part of a parabola that's cut off by a linear function here, in which case we could choose the order of integration and then tweak the limits. We could actually set this up using dx dy or dy dx, and we're going to see how that works as we do our work. I'm going to get rid of this for now though.